we're getting recorded right now. And so we were talking yesterday about exothermic and endothermic reactions. And I'm going to see if I can kind of get, let me get that to the side there so I am all set. So exothermic reactions. And if I call on you and you're like, dude, I don't know, it's totally fine. Let's see here. Nate Gerke, if you had to tell me a little bit about exothermic reactions, what do you know, man? And I may have picked Nate. We were having sound issues, so let's see. All right, I'm going to go over here to Martin. Martin, what do you know about exothermic reactions?
It's when heat is released in the reaction.
Okay, so we've got heat released. So typically exothermics are hot. We talk about the change in heat, the delta H. And since I am giving off energy, I'm losing energy, they are going to typically be negative in sign. And we talked about how we can represent these things if it's like A and B coming together to make AB. Because we're giving off heat, we're going to see some sort of a heat, some sort of an energy term over here. And typically that's going to be measured in joules or in kilojoules. One other thing that we talked about in the video that I put up yesterday and the stuff was an exothermic reaction is going to start out with a certain amount of energy. You're going to get up and over this hump, which is called the activation energy. And then because you are giving off energy, you're going to end up always with less energy than you have at the beginning. So if this is a graph of energy, E, versus, it's called the reaction pathway, but in essence, you just need to think of it as time. Okay, so that's just a quickie. Martin, I appreciate that. Let me go with either Liam or Chris Short. What can you guys tell me about endothermic reactions here? If we kind of mirror this information, would they be, tell me what you know.
Reaction that absorbs energy, right?
Okay, absolutely. Totally absorbing energy. So this one gives off energy. Gives off E, this absorbs E. Continue. Would we feel hot or cold if we touch an endothermic reaction? We would feel.
I have no idea.
That's okay. Chris, do you know?
I wasn't here for the last video.
That's all good, man. Chris, if exothermic is hot, what do you think endothermics feel like?
Cold.
Yep, absolutely. So we're just kind of compare and contrast these guys. The change in heat, all right? Whereas this guy gave off heat, what's this one gonna do, guys?
Gain.
It's going to gain. And so when you gain things, all right, that's a positive. So you're going to have a positive quantity for your change in heat. If we wrote it out as a reaction, we'd have A plus B plus our heat term, because heat is required for the reaction to occur, making AB. So you notice that the heat term shows up on the reactant side for endothermic, shows up on the product side for the exothermic. I want to just pause for a second, make sure. Am I losing anybody? You guys okay there?
I'm good.
Okay. All right. So we'll continue. And then the last thing here, and if you guys can mute there, I'm getting some extra sounds. That would be great. For an endothermic reaction, we're going to start out down low. We're going to have to get up and over a pretty big hill, and we get an overall increase in energy, all right? So this would be where our reactants are, and this would be where our products are. And so it is a gain in energy. All right, so let's move on here. And if anybody has an issue and they need to ask something, you just got to jump in and verbally say, hey, Mr. Caldwell, stop for a second, okay? Because I don't really know if you've got a question unless you speak up. All right, I got a cough here, excuse me. Hopefully you guys didn't hear that. All right, so this is representing another way of showing this stuff. So we had an exothermic reaction with that negative sign because it's a loss of energy. And we're seeing it here. Notice that the negative sign disappears because we never have negative signs in a chemical reaction, but it's showing up as a product. We're giving off this amount of energy, all right? Down here, it's an endothermic reaction, so it is gaining energy. That's why it's a positive sign. And since this is what is required for the reaction to occur, you have to literally put 264 kilojoules of energy into the reaction, right? here is the energy of your reactants. You have to put in 264 kilojoules of energy in order for this thing to happen, all right? So that's exothermic and endothermic. Now, what we want to focus our attention on today is combining the amazingness of stoichiometry with this new idea of heat, all right? So this is the
I'm sorry,
first.
Mr.
Yeah,
Colo. Can
Liam,
you go
go ahead.
back to your notes just real quick so I can take
Yeah.
a picture of it and write it down? Sorry.
Yeah, so you can totally do that, all right? Do you want me to, let me see if I can
No,
capture that part.
just at the top. Yep.
Okay. Whoops, sorry, hang tight. Are we good?
Thank you. I'm good.
Okay, all right. The magic and miracle of modern technology. Here we go. So check this out. So what we're going to start seeing is for this particular little unit. So here's our just traditional balanced chemical reaction. You know, nothing surprising. So 1 mole of hydrogen and 1 mole of chlorine is going to combine to make 2 moles of hydrogen chloride, hydrochloric acid. Now, as soon as we throw this in here, this is telling me that the change in heat as this reaction proceeds, based on what we just talked about, is this gaining energy or losing energy? What would you say, Dylan? Is this gaining or losing energy?
Is it losing?
Yeah, absolutely. So it's giving off heat. And so if I'm giving off heat, and Dylan, I'm going to unmute you there again. If you're giving off heat, is that an exothermic or an endothermic reaction?
Is it exothermic?
It absolutely is. All right, nice job. So what we're going to do is we're going to think about this in terms of what this actually means. So if I have 1 mole of chlorine, that's going to give off negative 185 kilojoules. This looks a lot like a mole ratio, but this number up here is not a number of moles. It's literally telling you how much heat is associated with 1 mole of chlorine. All right. Now we could also write that in the reverse direction. All right. If we needed it, depending on the conversion that we're getting ready to do, and you'll see what I'm talking about in a second. All right. For every 1 mole of hydrogen in this reaction, it's going to give off negative 185 kilojoules. All right. And then for every 2 moles of this, we're getting 185 kilojoules of energy released. So what we're doing is we're getting this idea that, you know, just like we did stoichiometry problems, which we're getting ready to tackle here, we can do stoichiometry using these heat numbers, okay? So if we wanted to go ahead and calculate the change in heat for this process, and it's giving me one number, 1 gram of chlorine, all right? You look at it and you say, okay, well, I want to know how much heat is given off, all right? Because I know that for every, 1 mole of chlorine, I should be giving off 185 kilojoules worth of energy, but I don't have 1 mole of chlorine. I have 1 gram of chlorine. So knowing what we know, we're like, oh, wait a second, I can convert grams of chlorine using molar mass into moles of chlorine. And then I can say, and I also know, based on this chemical formula, for every 1 mole of chlorine, I'm going to give off 185 kilojoules. So instead of writing what we used to write as sort of our mole ratio, we're using sort of this heat ratio. And then you just do the math that you know how to do. 1 times 1 times negative 185 divided by 70.9. So if I have 1 gram of chlorine reacting with more than enough hydrogen, that's how much energy that particular reaction would give off, all right? We could also do another problem where we said, hey, what if I wanted to give you an amount of energy to start with, and I wanted to calculate the amount of liters of hydrogen gas? Let me pause before I hit into this. Anybody need to ask a question before I plow forward here? I got Lauren and Liam and Chris and Grace and Dylan, and Chris Short and Martin. All right, I'm going to keep going unless somebody speaks up. So at this point we say, all right, now I'm starting with a known quantity of energy, and because it is liberated, that means that it was given off. And so that's why it's a loss, it's a negative. So this is how much energy I gave off. And then I just think, okay, well, I've got kilojoules right here. I need to have kilojoules in the bottom. Well, how many kilojoules? It tells me right there, 185 kilojoules. And because I'm doing this for hydrogen gas, I have to use the right number of moles of hydrogen gas, which was 1 mole of hydrogen gas. So for every 185 kilojoules of energy given off, that's going to be associated with 1 mole of hydrogen. 1 mole of hydrogen, because it talks about the liters, we use our magic number for liters, 22.4, and then that's the math. So look, that's the notes that I wanted to kind of run through. And then I wanted to do, if it's okay with you, maybe one more problem, because I think that, you know, I was talking with, I don't remember who it was, but someone was saying, look, it's helpful to kind of run through this with you, not face to face, because I wouldn't say that this is face to face, but at least it's a close attempt at it here. All right, so let's go ahead and do this. Let's go ahead and just say, and I know that this reaction is one that we've played with in some of these problems lately. So we got some N2 and some H2, and we're going to make some ammonia NH3, and we never want to work off of unbalanced equations. So we're going to go ahead and go 2 here, 3 here. And let's go ahead and say that the delta H, the amount of heat associated with this particular reaction, let's go ahead and say that this is a positive 56.2 kilojoules. All right. So these guys are all gases. All right. Excuse me, the hydrogen and the nitrogen are gases. This one, depending on the temperature, might be liquid. So let's go ahead and do this. All right. This one's going to be a little bit more complicated. Let's say that we have 12 liters of nitrogen reacts with, let's go ahead and go with 10 grams of hydrogen. And we want to find out how much heat is, and I'm going to ask a question of you guys, so think about this as you're writing. Because this is a positive quantity, is this going to be giving off heat or absorbing heat? And I'll take an answer from anybody that's willing to toss it out there. Is this guy absorbing heat or giving off heat?
Absorbing.
Okay, I'm hearing absorbing, and can you give me a justification? This is what type of reaction here?
Endothermic.
Endothermic, good stuff. So this is how much heat is absorbed. Beautiful. All right, now here's the problem. I've given you 2 quantities. Guess how many conversions we have to do?
2.
So we're off to the races, hopefully. We're going to go 12 liters of nitrogen, and we're going to convert that, 22.4 liters of nitrogen, into moles of nitrogen. And then the nice thing is these aren't as long a conversion, because at this point, I'm like, well, wait a second. For every 1 mole of nitrogen, I know that the amount of heat associated with that is this number, positive 56.2 kilojoules. Now I'm going to need you guys' help here, because I don't know that my calculator is super handy. I'm having to pull it up on the computer. So, you guys double check me here, because I may have really screwed that up. I got 30.1, and if I was going to sig figs, I'd go with 2 sig figs. Is anyone else getting 30?
Yeah.
That's what I got.
Okay, all right, cool. Thank you, Lauren. Thank you, Martin. I think I identified your voices there. So now we do the other one. We say, look, for 10 grams of H2, let's go ahead and remember that the mass of hydrogen is 1. So H2 has a mass of 2 grams. That's going to be 1 mole of H2. And then we're going to go back and we're going to say, okay, well, now wait a second. I've got to make sure that I'm using the right number of moles of H2. So for every 3 moles of H2, I'm going to, again, have to absorb 56.2 kilojoules worth of energy. And some of you guys that are quicker than me, you are already on this. Double check my numbers here. I'm getting something on the order of 93.6, which I would round to 94.
Yes.
All right. So at this point, which one do we go with?
Smaller one.
Always, all right? Because as nice as this is, yeah, 10 grams is going to get me 94 kilojoules of energy absorbed, but I don't need to absorb that because this is actually all the reaction that I'm going to get. So my limiting reactant, just to kind of remind you, was N2. My excess reactant was H2. And the nice thing is, you wouldn't have to do anything else. You literally just do the two conversions, you compare the heats, and you go with the smaller value. All right, so if you see one number, if it had only been the 12 liters, you just done the one conversion and you're done. If you see two numbers, you do two conversions, pick the smaller value. Okay. All right, that is a lot of stuff. I'm getting ready to take this one off here and just kind of check in with you guys. So I'm stopping the recording right now. And if I can get everything to work, there we go.